The broadcast is now starting. All attendees are in listen-only mode.
Hello, thank you for joining us today for the AWWA webinar on corrosion control. This series was initially slated for the 2020 International Symposium on Inorganics, so we're really happy to be able to bring this information to you in an alternate format. We'd like to thank our 2020 webinar sponsors, Woodard & Curran, Logistec Environment, and M.E. Simpson. I'm Kimberly Gupta, Water Supply and Treatment Manager for the Portland Water Bureau, and I will be your moderator for today's webinar. Here are some tips to enhance your webinar experience. We recommend that you close email, instant messengers, and any other programs not currently in use, as they may interfere with the smooth reception of the webinar, causing slide buffering and poor sound quality. Technical assistance can be found at the GoToWebinar technical support page at the link listed in your handouts and on the slide shown. As soon as you close the GoToWebinar screen to leave the webinar, a window will open with a survey questionnaire. We ask that all of you take a few minutes to answer the survey questions. Your feedback is important to us and helps us improve webinar programming. We encourage group participants to pick one person to enter collective responses to the survey and submit them to us. Before we hear from our speakers, I need to inform you that the mention of specific products or services in this webinar does not represent AWWA endorsement. AWWA does not endorse or approve products or services. All right, now for the main event, I'm really pleased to introduce our distinguished panel of experts for today's program. We have France Lemieux, the head of the Materials and Treatment Section for Health Canada Water and Air Quality Bureau, Bafu Lee from Dalhousie University, and Melinda Friedman, the president of Confluence Engineering. Our panel will be happy to answer your questions. Please feel free to submit questions anytime throughout this broadcast by using the question pane at the lower right of your screen. Please include your name and the name of the panelist to whom your question should be directed. Let's begin. France Lemieux will be covering considerations in updating the Corrosion Control Guidance document. France Lemieux is the head of the Materials and Treatment Section in Health Canada's Water and Air Quality Bureau and holds a bachelor's degree in biochemistry and a master's degree in civil engineering water resources. France's 32-plus-year career at Health Canada is multidisciplinary and varied in nature. She has worked in drinking water for 22 years, primarily as a drinking water treatment specialist. Although she has covered a wide variety of areas, including PFAS, Legionella, and DVPs, her main focus is corrosion control and inorganics, such as lead and copper. She has integrated information on distribution system and small system challenges into her work at Health Canada. She is a member of various U.S. and Canadian committees on health-based standards for drinking water, treatment units, and plumbing standards, chair of the NSF Additives Joint Committee, a member of the NSF Council for Public Health Consultants, and chair of the Water Quality Association's Public Health Review Board, as well as sitting on the board of directors of RISO, Center for Mobilizing Innovation. Her passion is working with industry, users, and regulators to collaboratively achieve positive public health impacts from safe drinking water. Take it away, France.
Thank you, Kim, and thank you everybody for joining us on a Friday afternoon, which I'm assuming in the US you guys have a long weekend, so this is pretty awesome for everybody to be joining us at this time of day, right before long weekend. So I'm going to give you a little, I'm having problems here, sorry. I get my cursor in the right place, it will help. So I'm going to give you an idea of what we're looking at towards when we're updating our corrosion control guidance document. I'll start with a little bit of history, give you an idea of what's in the current guidance document, what the drivers are for change, a little bit about our revised lead guideline, the focus of the update for the corrosion control document, as well as what's new and being considered. A little bit of talk about the lead variability. Boy, I'm having Kim's problem here, as well as total lead exposure, and give you an idea of what's coming next. A little bit of history. Our consultation document on corrosion control began way back in 2007, and we published a final document in 2009. Subsequent to that, there was a number of years before we actually got to updating the lead guideline, which was in dire need of updating since it had been published originally, not originally, but had been published in 1992, and they did an update, and that was finally done as the final update in March 2019. And at the same time, we revised the copper guideline, and it actually became a health-based guideline, whereas it wasn't before. Again, sorry, you have to be patient with me. So in terms of our 2009 guidance on corrosion control, it provides guidance on corrosion control programs and protocols, including for residential and non-residential buildings, as well as the supporting information behind that. Some of the principles of corrosion, such as the main contaminants that we focus on, which are lead, copper, and iron. We look at the sources, some of the factors that affect lead levels of a tap, for example, pH, alkalinity, stagnation, flushing, and the materials, and methods for measuring corrosion, as well as treatment and control measures for lead, copper, and iron. The other thing that we've done is identified contaminants that could accumulate and be released from the distribution system, resulting from changes in treatment processes, hydraulic regime, or water quality. We also included some action levels and sampling protocols intended to reduce exposure to lead through corrosion control. So it was not a direct impact on lead in the sense that it wasn't part of a lead guideline, but those action levels and the protocols are intended to sort of try to reduce those lead levels. And then, as I was mentioning, it wasn't intended to replace the guideline. The lead guideline itself was intended to complement that guideline. And that's key here. It's not, in the US, it's a treatment-oriented rule. For us, we have a lead guideline, which is health-based, and we have the corrosion control guidance to help achieve that guideline. So what's driving the need for change here? Well, our guidance was based on the previous maximum acceptable concentration for lead at 10 micrograms per liter, and that was developed in '92, as I mentioned earlier. And we revised that lead guideline, and that was finally published in March 2019. We have new information on corrosion control sampling and strategies. There's distribution system impacts that were recognized in guidelines for other metals. We had addressed it somewhat in the guidance previously, but there wasn't as much information as there currently is now out there. And there's a new copper guideline, as I mentioned, that was published in June 2019. So our guideline for lead, we've gone now to a MAC of 5 micrograms per liter, and we're looking at sampling for typical exposure at a populational level. And all of our guidelines are based on a typical exposure. So this is not unusual for lead. It is just the policy decision that was made some time ago for all of our guidelines. That lead guideline includes things like factors affecting exposure, some of the sampling considerations. We address lead variability and in particular particulate and dissolved lead, as well as some of the monitoring considerations. Just a little bit of a refresher in terms of the health effects for lead. We're looking at it as being an internationally accepted non-threshold toxicant by many agencies, Health Canada, US EPA, and CDC included. No safe level has been established for lead in children's blood. Lead exposure is associated with many health effects, but decreased IQ is considered the critical effect. I know that there is some discussion within EPA, I believe, that there are cardiovascular effects. Those are well known, but lead exposures that are most critical that we see are from the IQ decrease. It has the strongest evidence for a causal effect, and children have been seen to be affected even at the lowest blood levels that have been studied. In terms of exposure, we know that lead in drinking water needs to be measured at the tap if you want to get an idea of what people are exposed to. It's been published that lead service lines can contribute anywhere from 50 to 75% of lead in drinking water, and sometimes maybe more. But that doesn't exclude leaded brasses and lead solder, which can also have an important impact on the lead concentrations in drinking water, especially in buildings. And lead levels can be highly variable. In terms of sampling for our lead guideline, we looked at different sampling protocols, and because different sampling protocols will achieve different objectives, you need to sort of think of what it is that you're trying to achieve, because that's the important thing, is what are you looking at, what answer are you trying to get? And some of those protocols may actually achieve more than one objective, which is great in some senses and can be confusing to some people in other senses. So sampling protocols will depend on whether you're looking for exposure again, and whether it's an investigative or diagnostic type of sampling, what your treatment performance is like, and for compliance may be different than any of those other sampling objectives, sampling protocols rather. Sampling protocols should also capture the variability of lead because exposure varies obviously, and it needs to capture total lead, both the dissolved and particulate fractions, because if you're ingesting lead, it does not, your body does not make that distinction. You have a very acidic environment in which you ingest lead, and so the assumption is that there's a potential to absorb all of that, whether it's particulate or dissolved. So in terms of factors that are affecting lead release, we know that there are many of them, but typically they'll vary between particulate and dissolved. Dissolved lead is, based on water quality. Quite often the surface area of a lead surface, so the pipe length, the diameter, stagnation time of water, the release of dissolved lead is pretty well characterized, not completely characterized, but it's reasonably well characterized. Whereas particulate lead release is based mostly on physical disturbances, hydrant flushing, for example, road work, lead service line replacement, whether it's full or partial, galvanic corrosion, and hydraulic disturbances in the transport of particles. Some of those things seem obvious, but there are other things that are not as well characterized, and you may get particulate lead release and not have any idea why it's being released. So it's less well characterized. So what are we looking at in terms of our update on the corrosion control guidance? We're looking at protocols for assessing corrosion control. Our primary focus is going to continue to be on lead. It's not going to be the only focus, but is the primary focus in terms of the protocols themselves. We're reevaluating the document in light of the revised lead MAC, so it has to be a complementary approach, as I mentioned earlier. We're looking to update the information on optimizing and implementing erosion control, including the newest available information on orthophosphate silicates, anything else that's out there, and updating information on monitoring. We are also looking to see if the 90th percentile action levels are still appropriate. Do we need to relook at them? Are they even something that we want to keep? So those are the types of things we're thinking about. We're looking to update the information on sampling for different objectives. We'll look to expand the random daytime sampling information and the UK experience, because they have a significant amount of information out there on their experience with the random daytime sampling. Looking to update information for lead, copper, and iron, because those are three of the contaminants that are included in here that have had a significant number of changes. And we're looking to address impacts of accumulation and release in the distribution system, simply because there has been a significant amount of information come out lately, or in the last few years since we published that has an impact. We're also looking to make sure that we highlight the correlation between particulate lead and metals, and that metals can accumulate on top of iron and lead in the distribution system. Iron and manganese scales accumulate lead as well, so iron and manganese scales can be released after full or partial lead service line replacements, and that's going to be important information to include in that document, as well as the increased release of particulate lead. We have a lot more articles out there, a lot more data that supports that information. And also getting back to the tenet that, red water or discoloration events need to be monitored because they're not innocuous, because of this correlation between the lead and the metals, between the particulate lead and iron in particular. So it's something we've sort of had as a philosophy in the past, to make sure people understood that you need to sort of be sure that that's not just iron, but it's been a little bit more low-key, I think, across the board, and we've tried to highlight that a little bit more to make sure that people understand that it's not just iron that's in there. So what else are we going to be including in this revision? We're looking to reinforce the need to monitor in the distributed water, that is, say, at the tap, Again, as I mentioned, emphasis on the need to adjust the discoloration events because they are potential indicators of potential release of other contaminants, including radiological and other metals. Need to strengthen the information on issues that impact water quality. So the pH of the distribution system water quality, the importance of pH in corrosion control, the role of nitrification on pH, which we had previously addressed, but I think we need to sort of go back and make sure that that's complete, and the role of NOM, the natural organic matter, in the water quality. So really what we're looking at is a holistic approach in addressing these key related issues that have been identified in other documents as we progress through other documents in the past. In terms of monitoring, we're still looking to address residential sites, including single family and multi-dwelling residences. We need to consider what's practical, what's acceptable by the consumer. We should include buildings and schools, make sure that we're capturing those vulnerable populations. They were previously in the one, but we're keeping that and adding the information that's now, that's changed since then. And they also have different challenges than maybe a residential setting would in terms of fittings of faucets and bubblers that you might have to address. Looking to address the variability, the building type, the seasonal differences, the occupancy, water use, again, updating that information in terms of monitoring, and then targeting high risk zones and areas. In terms of monitoring, looking at the sampling type, the locations and the numbers to identify priority sites and locations, home with lead service lines, whether they're full or partial, need to be prioritized. Provide guidance on site selection when you can't sample with, at homes with lead service lines. Protocol for large buildings and schools. Large buildings, I'm not talking about office buildings. It's, we're not looking to drive corrosion control just for a larger office building, but some of these buildings have children in them, and so we're looking to make sure that they're captured where they need to be. But again, it is in the concept of the lead guideline, we found it difficult to assess a representative sample. So it's one of those things we need to make sure that we're doing a good job with respect to corrosion control. And again, it has to be realistic and practical for these larger buildings. In terms of sampling results, again, we're trying to address that in the guidance document and to have people understand what, that a sample result will tell you, what a sample result, can tell you really depends on how it was taken. So whether it was a 6-hour first or second draw, 30 minutes first or second draw, 5-minute flush sample, randomly time, profiling sample, they all have, achieve different objectives when you do those types of sampling. And then we'll be looking at the strategies to reduce lead. So obviously, the big driver is full lead service line replacement as the best approach, recognizing that it's not feasible to do in a very short period of time. This is a long-term plan. Partial lead service line replacement can reduce lead, and we want to make sure we get that message across that it may cause release of lead for several months afterwards, and that reduction might not mirror the percentage of line removal. So if you remove 50% of your lead service line, does not necessarily mean you will get 50% reduction in the lead concentration you get at the top. So those key messages need to get across to make sure that we try to promote the full lead service line replacement as best as we can. In terms of corrosion control, I think there's a recognition that it works reasonably well for a lot of situations, but in some cases it may not be sufficient to reduce lead concentrations when water supplied through a lead service line. So that's a recognition there. We know that this is a very, very challenging situation and a very challenging thing to do, and we're trying to make sure that people understand that there are things that they can do, and the guidance that we'll give will try to capture those essential elements, but sometimes it may or may not work depending on the water quality and a number of other factors. Other things that we've recognized in terms of strategies of reducing lead is sometimes you may have to go to things like low lead materials when it can be costly and difficult. So it's not our first go-to, but it's part of the strategy going forward, things that they can look at to see, what they can do to reduce the exposure to lead. And we've recognized that filters work well. They are a temporary measure, that they need to be certified by a third party as meeting the appropriate standard. for reducing lead under the NSF set of standards as well. Just for those of you who are not aware, then the NSF standard now includes a reduction to 5 micrograms per liter of lead or less in the standard. So we were able to get that as a committee change to mirror things going on both in Canada and in the EU. They're driving it towards the lower levels, and also with respect to some of the other issues happening in the US, people wanted filters that would reduce the lead levels lower. And the key messaging, of course, that maintenance of these filters is essential. So what's next? Well, we're hoping to get a document out to public consultation in early 2021, and we're working on the revision of the guideline, which is expected to start sometime in late 2021. So we're not there yet, but it is, and I say guideline because I'm not sure if it's actually going to have a health-based number or not, but it may be a guidance document. It will depend on whether there are any health effects identified. At this point in time, it doesn't appear to be a driver, but I use that as a generic term as an iron guideline. And we'll leave questions for afterwards, but I'm sorry, I didn't really have sound effects for that, but we do have a mailing list. We have a general notification list where we notify whoever's on the list that documents up for consultation or has been finalized. So if you're interested, you can certainly sign up and you'll get notified when we have new documents come out. Thank you again for your attention. I appreciate you on this late time on this day right before a long weekend.
Thanks, Franz, for that great presentation regarding the latest on the corrosion control guidance. I know that I, for one, always enjoy hearing what approach Health Canada is taking, especially as we anticipate the final revised LCR here in the States. So thanks again. All right, our next speaker is Bafu Lee. Bafu will be covering an evaluation of phosphate and silicate-based corrosion inhibitors using a pilot-scale distribution system. Bafu Lee is a PhD candidate and a Killam Scholar at Dalhousie University, Canada. He received his master's degree at the same university. His research focuses on the corrosion control of distribution systems and biological treatment. Take it away, Bafu.
Thank you, Kim, and thank you everyone to attend this webinar this afternoon. So today my topic is the evaluation of silicate and phosphate-based corrosion inhibitor using a pilot scale distribution system. So as we know, the phosphate has been widely used in corrosion control in drinking water industrial, and the major mechanism is to form a passive corrosion scale on the surface of the lead pipe. So when we talk about the phosphate in general can be divided into 2 categories. The first one is orthophosphate, and the second one is the polyphosphate. But in commercial product, we call it branded phosphate. So orthophosphate contains the only one orthophosphate unit. It is commonly used for corrosion control. But for the polyphosphate has a lot of different species, and it contains several orthophosphate units, and it's usually used for the sequestrations to solve the color or the turbidity problems caused by iron and the manganese. But the disadvantages of using polyphosphate is that it may increase lead released through complex lead with a polyphosphate molecule. So it's to the sodium silicate. Sodium silicate is well understood for sequestrate the drinking water, like the color and the turbidity problem caused by iron and manganese. But sometimes water utility also use sodium silicate to mitigate the lead released. But due to the very limited data and the studies, so the sodium silicate is not widely used in the drinking water industrial, especially for the corrosion control. So after carefully reviewing the literature in the past, we find some of the study report the positive result, but some of the studies report the negative result. So for example, in the 2005, microshocks indicate they observed a a decrease in the lead released by 50 to 95% when they switch the corrosion inhibitor from polyphosphate to sodium silicate. And in 2010, Lateral's report, they observed the decreased lead release to below 15 microgram per liter using sodium silicate when they tries to feed the branded salt water. So in the 2017, the Corrosion indicate no effective decrease in the lead released when they investigate the lead concentration in a galvanic lead pipe. And Wasinski in Halifax the report when she compared the lead concentration in the sodium silicate treated system, she finds the lead concentration is relatively high compared with the orthophosphate treated system. So in general, I think the discussion about the sodium application of the sodium silicate is controversial in the literature. So, and in these recent years, we can see some news about the failures of the distribution system using sodium silicate. For example, in Newark, New Jersey, the local water utilities, they used to use sodium silicate as a corrosion inhibitors to mitigate lead released from the mid-1990s. But even after a couple of after decades they used, the exact mechanism of the sodium silicate is still unknown. So the water experts think there are two possible mechanisms. The first one is the sodium silicate can form a thin gel-like layer, a protective coatings on the surface of the lead pipe, which can prevent the lead released. Another hypothesis is that when we dose the sodium silicate, it will definitely increase the pH, the water pH, which can decrease the solubility of the lead carbonate at most conditions. So the objective of my study is to evaluate the effect of the sodium silicate on lead released, and we compare the data with the orthophosphate treated system, which is the well-established corrosion control strategy. And we also investigate the silicate's impact on distribution system as a whole. So this slide shows the setup at the Pockwat Lake, Halifax, Canada. So we feed the filtered water from JD Klein water supply plant. Then we dose the chlorines and the three different corrosion inhibitors, sodium silicate, zinc orthophosphate, and orthophosphate. Then we adjust the pH to 7.5. Then the waters will go through a pipe loop system, which is made of PVC pipe or recovered cast iron pipe. Then the effluent of the pipe loops will went into the reservoir. Then we pump the water from the reservoir into one brand new full lead service lead pipe and a brand new partial lead service lead pipe. And the waters will be stagnant for 24 hours before sampling. So this is our experiment setup. So as we can see, there are 12 lead pipe, 6 full lead service lead pipe, and the 6 partial lead service lead pipe. So when we use this experiment design, we can identify the difference caused by the cast iron pipe and the PVC pipe, and we can also tell the difference caused by the different corrosion inhibitors. At the same time, that we can investigate the difference caused by the partial lead service lead pipe and the full lead service lead pipe. So this is the timeline of our experiment. So during the experiment, we maintained the orthophosphate treated system at 1 million gram phosphate per liter. Then we used the 12 million gram silicon dioxide to condition the system, and we investigate the median dosage of the sodium silicate at the 24 million gram silicon dioxide per liter, and we also investigate the scenario at the high dosage of the sodium silicate at the 48 million gram per liter. So this is our preliminary data. So as we can see in the orthophosphate treated system, in the effluence from the 4 lead service lead pipe, the lead concentration was in the range of 69 to 80 microgram per liter. But at the same time, we absorbed a quite high lead concentration from the sodium silicate treated system, which was 439 microgram lead per liter. The effluence from partial lead surface lead pipe is the relatively higher lead concentration due to the galvanic reaction. So in the orthophosphate treated system, the lead concentration was the 88 microgram per liter. However, the lead concentration in sodium silicate treated system was 613 microgram per liter. So then we summarize the data to compare with the difference between the galvanic reactions and the 4 lead service lead pipe. So as we can see, the galvanic reactions increase the lead release. So in the presence of the orthophosphate, the increase in the lead concentration was from 8 to 19 microgram lead per liter. However, in the presence of the sodium silicate, the increase in the lead concentration was 191. So we compare the increase of the lead with the galvanic current we measure between the copper side and the lead side. As we can see, the increase in the in the orthophosphate treated system, the 1 microampere only increased 10 microgram per liter lead per liter. However, in the sodium silicate treated system, 1 microampere increased around 100 microgram lead per liter. So it means the corrosion scale formed in the sodium silicate treated system cannot storage the lead release from the galvanic reaction. So this is the 2 photos that we take they are the corrosion scale formed on the surface of the lead pipe. So the left one is the corrosion scale appear in the sodium silicate treated system, and the photo on the left is the corrosion scale in the orthophosphate treated system. So as we can see there, the morphology is totally different. The sodium silicate treated system has the printed corrosion scale. And then we use the XRD, the X-ray diffractions to detect the crystal structure of these corrosion scale. So we identify this corrosion scale, they are the hydrocellulose, which is very common lead carbonate in the distribution system. And based on the XRD data in the orthophosphate treated system, we identify the corrosion scales is the hydroxylate pyramorphite, which is the very common lead phosphate solid. Lead phosphate solid, it usually appear in the orthophosphate treated system, which is the very low solubility. So let's come back to see the mechanism, because the first hypothesis is that the sodium silicate may form a thin gel-like layer of the coating on the surface of the lead pipe, because it may be very thin. So the technology we usually use in the corrosion analysis that maybe cannot perfectly match to analyze the coating. So we use another tool that is called the XPS. So it's the figure on the left that shows the XRD, the detect limitation. It can usually detect like around up to micrometers depth. So it gives us a bulk characterization of the corrosion scale. But it cannot detect the very top surface of the material. On the other hand, the XPS can detect nanometers level steps. So it can tell us the very good information on the top surface of the corrosion scale. So it can help us to have a comprehensive understanding between the water and the solid interface. As the figures on the right shows the percentage of the silicon, phosphorus, and the lead. In the sodium silicate treated system, we did observe the silicon-rich coating. The percentage of the silicon is around more than 95%. But in the orthophosphate or the zinc orthophosphate system, the percentage of the silicon is relatively lower compared with the sodium silicate treated system. But I have to mention that due to the lead concentration data we got, we do not have any evidence to say least silicon-rich coatings can mitigate lead release. So then we try to investigate the impact of the dosage of the silicon on the lead released. So we compare with the lead concentration at 24 milligram silicate dioxide per liter and 48 milligram silicon dioxide per liter. The result is is surprising because when we increase the sodium silicate dosage, we observed the increase in the lead and iron. So as we can see from this table, the cast iron surprised lead pipe. The increase in the lead was 505 microgram per liter. At the same time, we observed the increase in the iron, which was the 81 microgram per liter. But the PVC supplied lead pipes, the increase in the lead and iron is relatively lower, which was the 103 microgram lead per liter and the 23 micro irons per liter. So we suppose that the dispersed of the coil mantle from the corrosion scale on the deposit in the pipe loop system is the reasons caused the increase in the lead and iron. So we use another tool, it's called the field flow fractionation. For field flow fractionation can separate the mantles depending on the particular size. So it can separate like the dissolved lead and the coil lead or the particular lead. So as we can see the figure on the left, the red dashed line is the signal of the lead or irons that from the zinc orthophosphate treated system. We can see there is no any signal of the coil irons or lead. But in the present of the sodium silicate, we can see there is the two significant peaks of the coil iron and lead. The blue peaks is the coil iron, and the orange peaks is the coil lead. So the size is from 10 kilodaltons to 1 million dalton. So it is obvious that we did observe the high concentration of the coil iron and the lead at the high dosage of the sodium silicate. So in our previous study, I cite the two figures from the literature. So we find in the presence of the sodium silicate can increase the disperse of the iron. So we suppose that when we overdose the sodium silicate, the increased disperse of the irons can result in the high lead iron concentration in the effluent of the municipal pipe system. Then least irons is a stronger correlation with the elevate lead released in the full or partial lead service lead pipe. So let's go to the summaries. If independent of the pH, because in our study, we always maintained the pH of our system was 7.5. So at the same pH levels, sodium silicate cannot maintain lead concentration at an acceptable concentration, especially compared with orthophosphate treated system. And we did observe and thin silicon-rich coating at a nanometer level. But the silicon does not appear to form a protective corrosion scale like the lead silicon solid with lead directly. So for the high dosage of the sodium silicate, the overdosage of the sodium silicate may increase the coil irons and the lead. So it's quite important in the sequestration or the lead release control. Especially it will have the huge impact in the system which contain the unlined cast iron pipe. Because in our study, we are using the brand new lead pipe. So we suppose that it's still worth to investigate the impact of the sodium silicate on recovered lead pipe, which are rich in non-lead species, such as aluminum, calcium, or the magnesium. So finally, the presenters then want to acknowledge the support from the UNSEC Halifax Water Industrial Research Chair Program and its member partners, the fundings from UNSEC Collaborative Research and Development Grant with National Silicates and Cobrock Technology, and the scholarship support from the Killian Trust. So thank you, everyone.
Thank you, Bafu, for that interesting talk summarizing your research using phosphate and silicate corrosion inhibitors. Just a quick reminder, please submit your questions using the questions pane at any time during the live broadcast. Okay, now I'm very happy to introduce our final speaker today, Melinda Friedman. Melinda will be covering impacts of changing from surface water to groundwater on lead behavior, a desktop and pipe rig case study. Melinda Friedman is president of Confluence Engineering in Seattle, Washington. Melinda has decades of experience providing services related to source water and distribution system water quality evaluations, source water changeovers and new source introductions, regulatory compliance, comprehensive planning, and optimized distribution system and treatment practices. As a recognized leader in the distribution system water quality assessments, she has participated in numerous research and training efforts and has helped prepare many prominent industry guidance manuals published by the American Water Works Association, as well as the Water Research Foundation. Take it away, Melinda.
Thank you, Kim. I think this presentation will be a nice follow-up since we'll be looking at desktop and pipe rig studies looking at the carbonate system, pH and alkalinity adjustment, not the phosphates and silicates. So I'd like to begin by acknowledging the cast of characters that supported this project, beginning with the City of Tacoma, led by Kim DeFolo. They harvested the materials, constructed the pipe rigs, operated the pipe rigs, did the analyses, so they did a lot of the work. The project was managed by HDR Engineering and by Pierre Kwan. Confluence supported data analysis and looking at corrosion control endpoints for the water qualities. University of Washington, led by Gregory Korshin, to do the scale analysis, and then Steve Reiber provided some guidance along the way. So just a quick overview of the Tacoma water system for those that aren't familiar. We're located in the Pacific Northwest in Washington State. Looking at the map here, Tacoma is about a half hour south of Seattle in the Puget Sound region. And here's a photo of the beautiful Green River watershed. It's a protected watershed and was actually an unfiltered water supply for well over 100 years to the Tacoma area. I'm not sure if you can see down here, but that's the Howard Hanson Dam. And in 2014, conventional filtration was added to the Green River supply. Tacoma supplements their Green River supply with groundwater located in town. And that was sort of the focus of the study, was to understand how switching between surface water and groundwater might be impacting lead release. Now, the study was initiated in 2016 in the aftermath of Flint, when many utilities were proactively wanting to further understand the effectiveness of their corrosion control strategies and identify opportunities to further reduce lead levels. So this issue of switching back and forth was on Tacoma's mind and the focus of the study. This graph shows the history of 90th percentile lead levels in the tall blue bars. We can see, looking across from over the decades, that there were periods when the results were a little uncomfortably close to the 15 microgram per liter action level, and some looking for opportunities to improve. But when we look all the way to 2016, we see very low results of 2.1. Now this was post-filtration, after covering some open reservoirs, and activities that resulted in increased pH and chlorine residual throughout the distribution system. So many factors potentially contributing to those low numbers, but there was a lot of interest if that was real and sustainable and could be improved upon. And you'll also notice that lead and copper rule sampling had not been conducted during times of significant groundwater use, which is shown by the gray points in time. So we couldn't do a retrospective analysis to determine the impacts of groundwater on 90th percentile levels, hence the need for the pilot study. So this map shows, again, the overall of the coma system. The Green River filter plant's way out here, large pipelines bringing the surface water in, and then these red dots show where various wells are located in town. This large grouping of wells, the South Tacoma wells, actually all can be fed together to the north, or some can break off to the south, and then depending on which wells are operating, we can get different water chemistry out of that well field. So to try to understand the impact of groundwater and surface water, 3 different pipe rigs were constructed. One test rig was installed in this area, the Portland Avenue Reservoir, and this area always received 100% Green River surface water. So that was meant to be the control location. Second rig was installed at the Hood Street Reservoir Chlorine building, this building here, which actually we could be controlled whether the rigs would get 100% surface water or 100% well water. The groundwater from this grouping of wells comes through, and at this facility, it's pH adjusted, so the pH could also be controlled going into the pilot rig. And then the water goes into the Hood Street Reservoir, where a third rig was located at the outlet of the reservoir, where it could either look at 100% surface water and whatever blend was coming out of the reservoir. So the majority of my talk is going to focus on the pipe rigs located here, where the switching was between 100% surface water and 100% well water. Here's a look at the pipe rigs installed at the Hood Street location. Each of the pipe rigs consisted of harvested brass meters, copper pipe, and lead goosenecks. The City of Tacoma does not have lead service lines, but at the time it was estimated there were around 1,200 goosenecks, mostly installed in the 1920s, and the city has been actively locating and replacing them. And so, of course, these were an area of focus of the study to see how the lead was behaving in the switching of the water chemistries. So at Hood Street, the way the test was set up was phase 1, the entire test rig was equilibrated to the surface water, which had about a pH of 8.1. And after phase 1, 1 brass meter, 1 copper pipe, and 1 lead service line would be harvested and then sent to University of Washington for scale analysis. Then the entire rig was equilibrated to groundwater that was treated to a pH of approximately 7.4. And then another set of materials was harvested and sent to University of Washington for scale analysis. And then on this rig, it was converted all the way back to surface water. And then we did a final phase of groundwater treated at pH 7.8. Here's a look at the chemistry, the general conditions that occurred during the testing at Hood Street. A couple things to point out is that the pH difference that we talked about between 8.1 and 7.4 to 7.8 were the 2 treatment endpoints. The chlorine was pretty high at this location, and that's going to, of course, impact our results, and I'll talk about that. But I also want to point out the difference in the alkalinity and the dissolved inorganic carbon, the DIC. Quite a difference. This is very typical of the Pacific Northwest waters, where we have soft, poorly buffered, low mineral surface waters coming from those watersheds, and then more mineralized groundwaters. It's also important to note that there's very low iron in either of the supplies, and a bit of manganese, depending on which wells are operating, and there is sometimes seasonal manganese that comes out of the surface water supply. So here's a classic solubility curve that generated for these two waters in particular. The green line shows the solubility of lead as a function of pH in a low DIC water at a DIC of 4.8, and the blue line shows theoretical solubility of lead for the groundwaters. And we can see that because the DICs are different, lead isn't just a function of pH, the DIC really matters. We wouldn't want to match the pHs. If we just said pH is 7.5, then the groundwater would have lower solubility than the surface water, and at high pHs, the surface water is lower than the groundwater. But we're actually forming different lead species at the pHs because of the DIC. The groundwater is dominated by a cerussite, which is a lead carbonate, and as you can see in this picture, it's almost looks like quartz crystals. I took these from the internet. They're nice photos. And the surface water is a hydrocerussite, which is a lead hydroxycarbonate, and it's much more of a platy, flat crystalline structure that Bofu also showed a photo of in his presentation. So we're actually forming different lead minerals depending on which water is being served. That's what the solubility modeling predicts. And in fact, that's what we saw in the pilot rigs, as we'll get to. This diagram shows the results from the control rig at the from one of the goosenecks located at the control station that received surface water the entire time. So these black bars represent phases of changes that occurred at other locations, but not here. So this is surface water the entire time. You can see the red bars are dissolved lead, the blue bars are total lead, so the difference is particulate lead. Generally, we had decent replications across the many weeks, around 9 months of testing, with dissolved lead typically around 10 or under, and then variability in particulate lead. So this is the control. This is no changes, and this is some of the difficulty sometimes in working with pilot rigs is we do get variability even in our control rigs. That it can sometimes make it difficult to compare to your test rigs, but very important to have one control where nothing changes and you can see how it's behaving based on seasonal changes or operations that happen over the 9-month period. Now this is the test rig where we were alternating between surface water and groundwater at the chlorine building on one of the goosenecks, the remaining gooseneck, the one that stayed through the whole procedure. And interesting to note, in the first phase with all surface water, we had, if I flip back and forth, we had very similar results, around 10 dissolved between the control gooseneck at a different location and our test gooseneck at this location. So that was a good sign. Then when we switched to the groundwater at pH 7.4, as predicted, we do see an increase in lead results, both dissolved and particulate. And it takes several weeks for that to settle down. And when we always talk about it's got to re-equilibrate, what we're talking about when there's chemistry changes actually has to change its mineral structure. It's going from the hydrocerussite to the cerussite. And we see that it finally does settle down when we switched back to the surface water, and we get a very big particulate lead release at that time, because again, we've got to change crystalline structure. Can't really explain why dissolved lead was so low here. We did see lower dissolved lead in the control at that time too, but still more particulate than when we started. And then when we switched back to groundwater, again, a big particulate release and slightly lower dissolved lead at pH 7.8. This is again the higher groundwater, slightly better than what we saw at pH 7.4. So we see the actual results of these changes going from groundwater to surface water, particulate release, and scale predicted to be due to changes in the mineral structures. So how does this compare to our desktop theory, just in terms of lead solubility? The blue whether it's triangles or diamonds, these are all groundwater, and the green is the surface water. And we see pretty much the trend that was expected of the groundwater being higher lead release than the surface water at those pHs. We generally see that trend. But if we look just within the groundwater, which is just the blue, it's pretty flat line lead release across this whole pH range. 7.3, 7.4, all the way up to almost 8. It's pretty flat line, which is what theory would predict for the cerussite groundwater at this DIC level. There's maybe some improvement, but it's pretty flatlined. There were a few days when the wells were operating and a low DIC groundwater came into the plant, DIC down to 10, and that behaved almost more like a surface water with that low DIC, and we do see significant lead reduction at the higher pH. But for the higher DIC waters, it's some improvement, but not much. So it really did perform quite similar to how it would be predicted by the solubility. Again, this is just in terms of trends. The numbers in the solubility models are often much higher predicted. They assume equilibrium with pure lead surfaces and infinite contact time and all that kind of thing. So we get much higher numbers, but the trends are what we look for on the solubility models. Now there's another variable we have to add in, and that's oxidation reduction potential. We talk about that a lot. We use the Porbet diagrams to look at oxidation reduction potential, DIC, and pH. And these diagrams help us understand the thermodynamically stable minerals, species, the species of the metals that are thermodynamically stable under certain conditions. They don't tell us anything about concentration. They don't tell us anything about kinetics. It's just what might you expect to see given the conditions. So it's a function of pH, and this is actually voltage potential. This is
Hi, folks. This is Kim. I think we're having some technical difficulties here, so please bear with us, and we will get Melinda back on here shortly.
I guess I lost my audio there for a minute.
Perfect timing. It was right.
Am I back? Maybe everyone fell asleep when I got to the Porbet diagram, but
no, those are the best. Right.
All right. Well, we'll keep going here. Anyway, this diagram on this side was prepared for groundwater with a DIC of 23, and this diagram was prepared for surface water with a DIC of 5. And I think I was talking about the electrode, the ORP, where we measure the electrode potential of the water, which is pretty much controlled by chlorine residual in these waters. And again, we had high chlorine at these locations. And for the groundwater system, we predict that we would be forming cerussite and some platinurite. This is the more highly oxidized form of lead. As we move up here, we're in more oxidized forms. Lead 4 is great. That's the least soluble form of lead, and if we can form it, we certainly want to try to. Whereas in the lower DIC surface water, we'd be forming some sort of mixture of hydrocerussite and some platinurite would be predicted. So maybe this helps explain why Tacoma's lead levels were so low in last monitoring when they were able to have higher pH and more chlorine, and why we're seeing pretty low lead levels coming off of those pilot rigs as well. So then to tie some of the pieces together were the scale analysis when the sections were sent to University of Washington for visual examination, just to see how the internal surfaces appeared. Also to do scanning electron microscopy to look at some of the mineral phases and the characteristics of the corrosion scales. And then EDX work was done to determine the elemental composition of the scales. So in terms of visual examination, phase 1 on the top this is one of the lead goosenecks cut in half, and phase 2, where it's all groundwater, we can visually see that the scales had changed and were quite different. What we see in phase 1, the whitish gray, and in phase 2, the whitish grayish colors, typically the lead 2 carbonates, the cerussite and the hydrocerussite, and the brownish orange colors, while they may well be, could be iron manganese. In this case, that's actually lead 4, which can appear as a brownish color. And through the EDX work that was done, it was determined that the vast majority of the mineral compounds were lead, carbon, and oxygen, very low percentages of iron and manganese. So this was thought to be lead 4. And when we look closer in at the scales, this is at 1,000 times magnification and 5,000 times magnification. We do see these beautiful, perfect hydrocerussite crystals that form, minerals that form during phase 1, which is expected with the surface water. And on top of it is the lead 4 being formed. And I thought this was just so interesting because the lead 4 is actually, the chlorine is oxidizing the hydrocerussite scale to form lead 4. So that's exactly what's happening with the chlorine on top of these scales, forming a lead 4 coating, which reduces the solubility of the lead. Then under phase 2, the scales had to change over. We still see some hydrocerussite formation, but we see the development of these cerussite crystals, minerals, that when exposed to the higher DIC groundwater were predicted. These are more soluble at the pH that they were at, so that's why we saw higher lead release. We saw higher particulate release as the scales actually had to change their crystalline structure in exposure to the different chemistries. And here's just one more picture from the control building, a picture of the pipe loop there, pipe coupon. You can see it looked very similar to the phase 1 from the Hood Street building, where we had a lot of lead 4 in presence of in this case, which would in hydrocerussite, and you can see very clearly the crystalline hydrocerussite and all this lead 4 forming around and depositing around the scale. And I included this picture because after 100 plus years of being unfiltered, there's some diatoms trapped in the scale, so it's sort of interesting to see. So now just an update on where Tacoma is now. Since this study, Tacoma had targeted a pH of 8.4 for the surface water, so sliding the star down a bit to be even lower on the lead solubility curve. Groundwater pH of 7.8, just to ensure they're in the flattest part of the curve. And they've been targeting a chlorine residual of 0.8 through the distribution system, and their 2019 monitoring, the 90th percentiles were non-detect for both lead and copper, which is really amazing. That means their 90th percentile was less than 1 part per billion for lead. And of the 51 samples, only 4 had detections. The highest detected value was 4.8. Now, once again, because of operations, there was no groundwater on at the time of sampling, but I think the city can be rest assured that they've optimized the treatment between targeting the pH and chlorine for the DIC of their groundwater, so that levels will be as low as they can go, and they're truly optimized. So to summarize key findings and recommendations, switching between surface water and groundwater can impact lead release. It impacts the lead speciation. It can increase particulate release. We have to really understand that's important. It's very difficult to ever reach equilibrium if we're switching often. So wherever we can provide consistent supplies and avoid that switching is going to really benefit our corrosion scales. It's not enough or even necessarily appropriate to just try to match pH. Groundwaters and surface waters will form different mineral species depending on DIC and ORP, so it's not just about pH. Now, of course, stable pH is very important for many distribution system reactions, and it should be a goal within a certain supply area, a certain zone to maintain as stable a pH as possible. But for corrosion scales, we have to think about more than just pH. I've talked about alkalinity and DIC, but I never mentioned buffering capacity. We have to think of these parameters beyond buffering capacity. They obviously play a major role in which dominant species are going to form in the water. Chlorine residual plays a major role. We can form some lead-4, that's great. It has much lower solubility compared to lead-2. But since it's very difficult to control chlorine levels within premises, within buildings, after stagnation, we must do everything we can to optimize for lead-2, which is just what we did here with Tacoma. But if we can form lead-4 while balancing disinfection byproducts, maintaining customer acceptance, it can certainly help reduce lead levels. Multiple tools were used in this study. They all have value. Very important to use them all where you can. The desktop modeling, pipe rigs, and scale analysis tied together very well here. There's also bench testing that can be done with coupons that can be very informative as well. We did not do that as part of this study, but been a great tool in other studies. And for this study, with using the carbonate system, theory matched reality very well. This was an incredibly well-behaved system with the carbonate theory. It's often seen in Pacific Northwest waters, but isn't necessarily going to be the case elsewhere. But please use these tools. Let's learn what we can, share results, and get us all optimized. So I thank you. That's the end of my presentation.
Thank you, Melinda, for that excellent talk highlighting the potential implications to lead speciation when switching from surface water to groundwater. It's really good stuff. Thanks again to all our presenters for their great presentations. And now I think we have some time for Q&A. So we'll just go ahead and get started here. First question is, sorry, let me adjust. First question is for Bafu. For the pilot study, what was the range of DIC and alkalinity? Also, what was the variability of pH and chlorine? And Bafu, if you're talking, you are muted.
Oh, sorry, I muted. So the water quality in Halifax is the low DIC, low alkalinity, is low alkalinity. So I think the DIC concentration in my study, I think it's around, I think it's below 5 milligram per liter. So alkalinity is around, I think it's 5.3 calcium carbonate, but the feed water's pH was the 5.5, but in the model in the pilot scale experiment setup, we adjust the pH to 7.5. Yeah. Okay. So
great, thank you. Okay, our next question is from Melinda. Melinda, do you have concerns about increased iron corrosion if the buffer capacity decreases due to the higher pH?
Oh, no. Well, in theory, yes. Moving up to 8.4, you're at the lower part of the buffering capacity curve. But for waters of this low DIC, that's the whole range of 8.2 to 8.5 is all pretty much the same for buffering capacity. We really don't see much of a change there. Plus, Tacoma did increase their alkalinity a bit, going from the 20 to 25, maybe 25 to 30, to try to adjust for potential impacts there and to try to maintain that pH out to the tap.
Okay, great, thank you. All right, next question. I think this is also for you, Melinda, but other folks feel free to join in. Will the 0.8 milligram per liter chlorine residual actually be capable of forming a lead-4 species? Is lead-4 actually relevant in the system as opposed to the pilot test?
Yes, yes. The surface water that was in the pilot rig had a residual of around 0.8, and we did see the lead-4 in the pilot rig at that chlorine residual. And yes, we believe that it is contributing to the extremely low lead levels that we're seeing out in the distribution system. Again, we can't rely on it, and it's not one of the optimal corrosion control treatment strategies in the existing or in the proposed rule because it can't be relied on since chlorine is so reactive. But between filtering the supply, removing natural organic matter, lowering the TOC, we've seen incredible improvements in chlorine stability throughout the distribution system, where it makes it a more viable approach. And yes, I do think it is contributing to the very low levels we're seeing.
Great, thank you. This next question, I think, is for the entire panel. How much lead is there in PVC pipe percentage range? I'm not totally sure. Oh, go ahead.
Teresa Mew here. I can sort of address it to a certain degree. PVC pipes don't typically have any lead in it. In the past, I think some of them were cured with some lead acetate, and there was some residual lead left after processing or manufacturing, but that now is not allowed, and certification ensures that they're not seeing lead in PVC pipe.
Great, thank you, Franz. This next question is actually for you as well. Will Health Canada be considering water quality parameters as a surrogate for TAP sampling? And why is RTD sampling being considered for inclusion into the guidance?
So with respect to water quality parameters, there's a use for them. They are very good in terms of process control and making sure you understand what's going out into your distribution system and maintaining that water quality. They are not a surrogate for lead. You cannot predict what your lead level is going to be at the tap based on water quality parameters. So there's a use for them, but it's not something, in order to be able to see what people are exposed to, you really need to be sampling the lead at the tap. There's no surrogate for that. With respect to random daytime sampling, the difference between now and when we first published the Corrosion Control Guidance document was really the fact that the UK experience has been well documented. There's a lot of information out there, and we feel that this is a potentially practical way to get a sense of not only from an exposure standpoint, but also from a corrosion control standpoint, because it's being used for both, and it's one of those sampling protocols which has the possibility of being used for more than one objective. So from that perspective, it's good. The downside, of course, of RDT is that you need much more sampling to happen, and it is, as with a lot of the exposure sampling, it's not intended to represent sampling for an individual, but rather an area or a zone and a population level sort of exposure. So I think it's a useful tool. Like there are other useful tools as well, but I think it's a useful tool that we really hadn't had a lot of information on when we published it in 2009. But I think there's enough information out there for us to be able to bring that forward.
Great, thank you. Next few questions are for Bafu. First one is, what is the difference between the brand new lead pipe used in your study and the recovered lead pipe in your suggestion?
In our study, we used the brand new lead pipe, which is different from the real scenario, because we suppose the result from the brand new lead pipe is repeatable and the result is universal. But considering the real scenario, like there are a lot of different non-lead species can accumulate on the lead surface lead pipe. So I think the case about the recover lead pipe is the different water utility. They face the different kind of the corrosion scale. So I think so these are reasons when I say it's in the future study it's worth to investigate the interaction between the silicons to recover lead pipe, because it may work very well in maybe some water utility, but for another water utilities, because the corrosion scale is different from others, so the silicon may not work very well. Thank you.
Okay, thank you. Bafu, this next question is for you as well. Lead results were significantly higher for cast iron versus PVC in your study. Did the lead come from the cast pipe itself, especially since it was new, or is there a more complex interaction happening?
I think the reason is when we, I think the first one is the difference between the cast iron pipe and the PVC pipe is the cast iron pipe can release the iron. So in the previous study, it has been proved that there is a very stronger correlation between the irons and the lead. And in my studies, especially at the high dosage of the sodium silicate, I think the sodium silicate dispersed the iron from the cast iron pipe, so which result in the pretty high concentration of the iron. Then when these irons get into the lead pipe, then it brings a lot of I mean that it result in the increase in the lead.
Okay,
Yep.
great, thanks.
So, yeah.
This next question is for the entire panel. Do you have any thoughts on the effects of higher temperatures on lead solubility in the southern U.S. versus the northern U.S.?
Well, temperature is an important factor in lead solubility, but I don't think we've whenever we do the pilot rigs, we're trying to do them at the actual temperature of the water or the building that we're in. We do see seasonal impacts, but I guess I can't really speak comparing North U.S. to South U.S. Maybe someone else has some ideas.
I can't speak to that, but I do know that, there's a seasonal sort of impact, whether it's a pure temperature or other things that come into play. I would agree with you. I don't know that there's a very distinct, clear temperature only effect. And I would assume that the variability in water temperature in the south of the U.S. wouldn't be significantly different than maybe summertime temperatures in the northern U.S., but the big difference would be obviously over the seasons.
Okay, great, thank you. This next question I think is for the whole panel as well. I'm wondering how well iron corrosion and lead corrosion is correlated based on your knowledge. Is iron corrosion monitoring useful for lead concentration control?
I think for my personal understanding is because the municipal pipes that some of them contain the pretty old corroded cast iron pipe, but some of them, like the new community, they are maybe using the PVC pipe, so they do not have this problem. But when the cast iron pipe has been corroded, so it can release high concentration of the iron, and these irons that can maybe absorb or the complex with the lead in the lead service lead pipe. So if we observe the high concentration irons, that sometimes it can result in the high, unusual lead released. So yeah, this is my personal understanding.
And I wouldn't suggest that it would be useful as a replacement of lead sampling itself. I think it's a good indicator that there may be lead present, because it is, as Bafu indicated, it does get absorbed by the iron. So in terms of iron, it goes back to the principle that if you've got iron in your water, then you may have lead as well, and it may be a useful indicator, but it certainly wouldn't be something that I would recommend sampling for instead of sampling for lead. It's, as Melinda indicated, there are a number of tools you should be using, and that could be one of them as well.
I would add too that there's probably different answers to that question, whether we're talking about distribution systems versus premise plumbing. In either case, I agree, we would never substitute iron sampling for lead or other parameters if we're trying to understand lead corrosion. But we do a lot of work with main cleaning and correlating, metals accumulation on surfaces and pipes, and we do see lead occurring in distribution system pipes. But in a situation where you have lead service lines feeding maybe galvanized plumbing, you could have quite high concentrations of lead on that galvanized plumbing, and if you're getting discolored water in those buildings, there could be more significant lead release there. So it is important to look at the whole picture and they can be related, but yeah, agreed that I wouldn't substitute. I would just add maybe iron as an indicator in a system.
Great, thank you, 3. Okay, we have one last question here for Bafu. Do you have any suggestions for the water utilities, which are using sodium silicate for corrosion control or water sequestration?
So as I know, not too many water utility they are using the sodium silicate for the corrosion control, but I think when I read some documents that I find many Canadian water utility they are using the sodium silicate for the sequestration. So I think my suggestion is that when we use the sodium silicate, no matter for corrosion control or the sequestration, we need to carefully to evaluate the dosage. Because, for example, if we find some fallings that in the pH in the salt water, sometimes maybe water utility they will increase the dosage, but the overdosage may result in the increase in the disperse of the mantle. So I think the carefully evaluate the dosage and tries to understand the mechanism is quite important for the industrial.
Okay, great. Thank you, Bafu. So this concludes the question and answer portion of today's webinar. Thanks again to our panel for today's excellent presentations on corrosion control. This concludes our webinar on corrosion control, but before we go, AWWA hopes that you join them for the conclusion of the Contaminants of Concern, Managing Lead and Manganese webinar series. The final webinar is Strategies for Understanding and Managing Risk from Lead, and it's on this coming Tuesday, May 26th from 1 to 2:30 Mountain Time. And if you missed any of the previous webinars and have not purchased the series bundle, there is still time. You can upgrade and get access to archives of the entire series. And I might be biased, but I think it's a pretty great series, so I encourage you to do so. On behalf of AWWA and specifically the Inorganic Contaminants and Inorganic Contaminants Research Committees, I want to thank you for joining the webinar today. Please don't forget to participate in the survey immediately following the webinar. We look forward to seeing you at our upcoming events. And until next time, thank you for keeping the water safe and secure. Goodbye, everybody.